Okay, now I'm going to look at the problem of doing a partial fraction expansion in the case where we have complex roots. Now there are two procedures that people usually use when they're trying to find the partial fraction expansion for complex roots. Um, One is to treat it just like we do in the real root case, and that's what I'm going to do here. The next video will deal with the alternate method. So let's look at this function here, f of s, and s is s plus 3 divided by s plus 5 times s squared plus 4s plus 5. Now we want to factor this part of the denominator to write all the factors out for the denominator. But this polynomial right here has complex roots. These complex roots are written here. S plus 2 minus j times s plus 2 plus j. Now, the term j here, as you'll see, is alternately and often used for the complex constant. Up until this point, we have used the term I for the complex constant, but among engineers, they usually use J instead of I. So you will find these two notations, and you should be familiar and comfortable with using both notations. So we just treat this like we do in the real root case. We say, okay, we have this function right in here, and it has these three factors in the denominator. So we write it like a1 over s plus 5 for the s plus 5 factor, plus a2 over s plus 2 minus j for this factor, and then plus a3 for s plus 2 plus j right here. And what will turn out, we will find, is that the A2 and A3 terms turn out to be complex conjugates of each other. Now, we proceed just like we have before for real roots. We find A1 by taking the factor. A1 is the numerator over S plus 5. We take A1 multiplied by f of s by s plus 5, and then we evaluate at s equal negative 5. In other words, we evaluate right where this term is equal to 0, which is s equal to negative 5. And by doing that, we evaluate for A1. We find A2. We take s plus 2 minus j times f of s, because this is the denominator term for the A2. Okay, and then we evaluate where this term is equal to 0, and this term equals 0 when s is equal to negative 2 plus j. S equal negative 2 plus j makes that whole expression there equal 0. Similarly, we solve for A3, and as I said, we find that A3 and A2 are complex conjugates of one another. So here I go ahead and I solve for A1, A2, and A3 using that procedure. And it's a pretty straightforward. For example, A1 is just equal to s plus 3 divided by s squared plus 4s plus 5. Let me put that in there. And then we evaluate at s equal negative 5, and we get negative 2/10. And then we solve for A2 and A3 using a similar procedure. So we can write f of s using those values for A1, A2, and A3, and this is what we get. We get this term right in here. Now, the only thing that might be bothersome here, now, for many applications, when you're doing partial fraction expansions, this is, in fact, right where you might like it. You might like to have these complex terms here. But let's say we want to simplify this, and we do that by multiplying numerator and denominator here by the complex conjugate of the denominator. We want to get these complex constants out of the denominator. We do the same thing over here. We multiply numerator and denominator by the complex conjugate of the denominator. So in that case, what we have for our f of s is we first term remains as it was, and then we have the second term here where we've multiplied numerator and denominator by s plus 2 plus j, okay? Because s plus 2 plus j is the complex conjugate of this denominator term. Similarly, over here, we multiply numerator and denominator by the complex conjugate of the denominator. That's what we're doing right here. And as we multiply these two terms together, because they're multiplying complex conjugates, the result is we get a factor which is only real, which is this thing. Now here we have to multiply real part by real part, and then we multiply imaginary part by imaginary part, which gives us a real result, because the j times the j is -1, if you remember. So we write this down so we can group the real parts together and group the imaginary parts together. And we do the same thing over here. This times this just gives us the same denominator, s squared plus 4s plus 5, that we got over here. But here again, we have to group the real parts together and the imaginary parts together. Now, because now both of these fractions have the same denominators, we can now combine the two fractions into this big term right in here, which I couldn't barely fit on the page. So we get this whole big term here, which has this plus this in the numerator. And then we proceed to simplify, algebraically simplify the expression. And as we do that, the imaginary parts disappear. They all cancel out to 0. And we're left with this expression right in here. So this is what we get if we simplify this function right up in here. And so this is a summary of the first way of dealing with complex roots on a partial fraction expansion. Okay, the next video deals with treats another way of solving the same problem. Until next time.